Hi, this is Alkin for Technaid Research Digest. This is a podcast where we talk about CAD technologies related to exoskeleton and motion capture systems. As a research and technology company, we are interested in knowing emerging research, especially from our partners or colleagues. So today I have the pleasure of introducing a colleague and a friend of the house I met a few years ago at the University of Waterloo, and now is currently working at the University of Toronto. So I want to introduce Dr. Brokoslaw Laschowski. Hi, Brooks. How are you today?
Hi, how are you?
Great, great. It's a pleasure to have you here. You accept our invitation. It's really good to talk about your subject. I mean, exoskeletons. I think it's a topic you are really in right now.
Yeah, I appreciate the opportunity. And like both of us, we're obviously working in the space, and so it's always fun and interesting to be able to talk to other people in the field. So
Yeah, definitely. So I want to start knowing a little bit about you and how you start working with with exoskeletons. I mean, how you start saying, well, I want to start working with exoskeleton. What's your background with this?
well, exoskeleton research is pretty multidisciplinary. Like it requires, because these are devices that are worn by humans, often research labs that are conducting this type of research have clinicians, they have scientists, they have engineers, and engineers of many different disciplines: mechanical, robotics, electrical, mechatronics, and even on the human side, there's physiotherapists, occupational therapists, physiatrists, sometimes nurses. So there's a lot of different people that are involved in this type of work. My background is pretty multidisciplinary as well. I actually have advanced degrees in both the human side, so kinesiology, motor control, neuroscience, but then also degrees in mechanical engineering, biomedical engineering, kind of computer science, robotics. And I think having background in both the human side as well as like the engineering and technology side really kind of benefits. So yeah, if you're interested to know, like, I guess like some of my formal training before we met during my PhD, my undergrad was in kinesiology at the University of Toronto. I then did my first master's degree in kinesiology with a focus on biomechanics at the University of Western Ontario. And then I did a second master's degree in mechanical engineering. And that's kind of when I started really getting involved in some of the work that I've kind of started to specialize in later on. So during my master's, I did a lot of work in modeling and simulation of biomechanics. How do we design kind of optimal control models to simulate how do humans control movement? And that was a lot of fun. We did a lot of predictive simulation work, and some of that work was specifically targeting people with neurological impairments. So those who are wheelchair bound due to like spinal cord injury, for example. And that work ultimately motivated me to get into the field of wearable robotics, so exoskeletons and powered prosthetic legs, as part of my PhD. And that's kind of where you and I met at the University of Waterloo. We were quite interested in this idea of control and how do we improve control of some of these devices? How do humans interact with these kind of robots? And control plays a big part of that. Now in Canada, we don't have an extensive history in exoskeleton research. And so unlike say the States or some places in Europe, and so I would say that we don't have access to a lot of in-house hardware. And so I guess that's kind of where we met, where we were looking at various commercial exoskeleton companies, Technaid being one of them. And yeah, that's kind of how we met, be able to use your exoskeleton as a research platform for us to explore some of our control, but then also some of our design principles as well.
Yeah, that's amazing because I remember when you were performing your experiments, and yeah, our device is mainly used for researcher by researcher actually.
Hmm.
All we want to know is what's the level of control you want to create. And we have some developments in a low, medium, and high level depending on what's the necessity of the research. In your case, what do you expect, or what do you think you expect with the exoskeleton to control?
Like, what do I hope for, or like what were
Yeah,
we
yeah. For
working on?
example,
Or
yeah. I mean, when you start working with the exoskeleton, I remember you start trying the sit down and stand up. This
hmm
is a high, let's say, a high level where you perform some decision. So, what do
hmm
you expect with this kind of control?
yeah, like as you pointed out, not all, but most exoskeletons are governed by some like hierarchical control architecture, where there's a low-level controller, which is just like standard engineering. Like these type of control principles have been around for a long time, like trajectory tracking, like local closed-loop feedback control. Um, Mid-level control is kind of specifying for a given activity what is kind of like the optimal level of assistance, and there's a lot of work being done in that space right now. Like optimal assistance profiles is very challenging. Even just theoretically, like what is considered optimal? Like what should the robot do to assist the user? Like what does the user want out of the robot? It's not even quite clear, and there's a lot of people working in that space. Um, I think a really cool area for mid-level control is using reinforcement learning to be able to try to automatically learn some of the uh, optimal control objective functions that the user may want to do when interacting with the exoskeleton, and then use that as a control objective. I haven't transitioned to that, but it would be nice to eventually move into that space. A lot of my work focused on high-level control, and high-level control is essentially if you have these low-level controllers that are mode specific, you then have to have some type of, or presumably you have to have some type of high-level controller to uh, be responsible for decision making and switching between these different types of modes. And this is how a lot of research is being done right now. There are some researchers out there that are working on trying to control over continuously varying activities, and that's really cool. Where now we don't have this need to use classifiers to classify and then switch between different activities. You can then control over continuously varying activities, and that's really cool. But that's still very much in its preliminary stages. Um, so with high level control, like I said, most exoskeletons, especially commercial ones, are divided into different types of modes. You'll have a mode for walking on level ground. You'll have a mode for walking upstairs. You'll have a mode for sitting down. And there is this need for switching between them. Now, especially in the commercial space, because we don't have really robust automated controllers yet, a lot of commercial exoskeletons, maybe by just default, have to use manual control in order to facilitate safe usage with the exoskeleton. So, like for example, Technaid, you do use a mobile interface in order to allow the user to effectively communicate what they want to do to the exoskeleton. So they would then specify within a user interface, typically on a mobile phone, what do they want to do? Do they want to walk forward, and how fast do they want to walk forward? There are some other commercial exoskeletons that use kind of exaggerated movements performed with the exoskeleton, maybe like swaying back and forth. Some use joysticks. They're all some form of manual control. Now, it would be nice to possibly give the option of having more semi-autonomous or autonomous controllers where the user doesn't have to consciously think about controlling the device. The robot can make control decisions for itself. Now, commercial devices don't necessarily offer that. Can't offer that right now, probably because these are still experimental. And whenever you're dealing with exoskeletons, user safety is the utmost important. And so as we're working in the research labs right now to develop better autonomous control systems, eventually we may get to the point where we then can start commercializing them and then deploying them in commercial hardware like the Technaid exoskeleton. So on the autonomous control side, prior to starting my PhD, virtually all research was being done using sensors that are either on the user and or on the robot. Now, these include things like IMUs or position sensor, EMG, even EMG, position encoders, something like this. And so one of the things about these types of sensors is that they can provide you information about the current state of the user and or device. So it can tell you what the system is currently doing. It doesn't necessarily have the ability to project into the future what does the user might want to do in the future. And so it has a very limited prediction horizon, we can say. And so the analogy I usually give is it's kind of like the automated controller is kind of like walking blindfolded. So when I started my PhD, I thought it'd be really cool to explore area of computer vision. And there have been some research around that time being done in computer vision where they're trying to integrate wearable cameras within the control of an exoskeleton or a robotic prosthetic leg. But virtually all of these computer vision systems, for classifying the visual data that's being selected or that's being sampled, they use kind of traditional statistical pattern recognition and machine learning. And these types of algorithms require manual feature engineering, where the user has to hand design the features within the image that can be classified using a classifier. Around 2012, in the kind of the broader computer vision field, deep learning came on the scene, where people started exploring the potential of using convolutional neural networks to automatically and efficiently learn the optimal image features directly from training data. And they received enormous success within general image classification. And so when I started my PhD, I thought it might be interesting to explore this area of applying deep learning for computer vision for exoskeletons and prosthetic legs. And so around that time, we were kind of one of the first to do that, where we're allowing we essentially gathered many images and we trained a neural network model to be able to predict the environment, the walking environment in front of an exoskeleton user. And we achieved like a pretty high classification accuracy, which is great. That's what you want to promote user safety. And we received a lot of attention from it. It seemed to really spark the interests of the research community. It was nominated for some pretty prestigious awards. And this kind of motivated us to, not the awards, but like the general excitement and the promise of using computer vision kind of motivated us to continue exploring this. And that's kind of how it went. Like this led to a very large project of developing computer vision systems that are powered by deep learning to be able to recognize ever more complex environments. And that was one of the focuses of my PhD. And the Technaid exoskeleton, it provides a nice platform for that type of research because the control architecture is open. So in our case, we're focusing on computer vision. So this allows us to be able to evaluate how our computer vision data can be integrated within an intent recognition system and deployed within the Technaid exoskeleton, for example. Not all commercial exoskeletons offer a feature like that, where you're able to directly connect to the controller. Probably because most exoskeletons are designed for clinical use, not necessarily as research and development. And I do believe, you correct me if I'm wrong, there are some other researchers that are using the XOH3 for we're integrating neural interfaces and seeing whether or not like information directly from the brain can be used within the control of the Technaid exoskeleton, if that's correct.
Yeah, that's correct. Actually, it's a research group here in Spain. They're using EEG signals and predicting what's the intention of the patient and send a command to the exoskeleton. Also working in a high-level control.
Yeah, the same thing.
Yeah, it's quite similar. I think it looks like even if you are working in a high level, there are many hierarchical levels there where you can work. I mean, this classification, this decision process, you can split in another kind of levels. So it's really awesome because one is computer vision, another is brain interfaces, where you can predict and send these kind of parameters. It's really cool.
Yeah, I'm glad it's nice to see that the Technaid exoskeleton has been deployed like really completely totally opposite ends of the spectrum, where the group in Spain, they're working on neural interfaces to allow the user to directly control the exoskeleton just by thinking. And we're working on the complete opposite side, where we want the robot to do all of the decision making. So we're taking inspiration from autonomous vehicles and autonomous walking robots and integrating computer vision and deep learning to allow these exoskeletons to control themselves. And so it's interesting that the same hardware, the same exoskeleton is being used for completely opposite ends of the spectrum in terms of control signals.
Yeah, who is performing the controller there? Yeah, you're right. But I'm thinking about this field you're working right now. I don't know if you have seen the new rules of the Cybathlon. When I was reading about this, I said, "Oh, that's all about the environment. You need to know what's the test bed, and how to perform, because you have to use a different kind of controller depending on the activity you need to perform." And I remember your research, your paper about this detecting scenarios, and that's the key. We need to use wearable cameras or another kind of sensor to detect really accurate what is the task.
Yeah, it's interesting that you mentioned that because, well, for listeners of the podcast, if they're not familiar with the Cybathlon, it's a really interesting event where it's perhaps analogous to the Paralympics, where you're showcasing high performance in individuals with physical disabilities using assistive technology. But the difference in the Cybathlon is that it's powered assistive technology. So instead of using a manual wheelchair, it's a powered wheelchair. Instead of using a running prosthesis like you would see in the Paralympics, the users will be using a powered prosthetic. And it's really interesting. I believe it was originated from a group in Switzerland. And
Zurich, I think.
Zurich, yeah.
Zurich.
And they actually reached out to me, I believe late last year, and they were interested in our computer vision system and what we're developing, and wanted to connect us to the various teams that are competing within Cybathlon. And so there are some teams that are competing within it's like the exoskeleton race. So they have a user wear various exoskeletons that are being developed in, I believe, both research labs as well as commercial companies. And they have to navigate a very challenging terrain, and performance is evaluated based on a number of things. Speed and time to completion is one of them. And the ability to be able to integrate computer vision within some of these automated controllers does have the potential to improve performance of these exoskeletons during this kind of rough terrain race. They have to go up and down stairs. They have to step on specific locations within like a platform. And so, it's interesting that you mentioned that, because they actually did reach out to us. I believe it was late last year, and just wanted to inquire more about our system and to see whether or not we would be interested in talking to some of the various teams that are going to be competing.
Yeah, it's really exciting. I mean, in my point of view, it's really exciting to know that this kind of challenge improve the technology because it started working in the new challenge, new ways to use the exoskeleton, what's the real needs of the patient. Uh, I'm really excited with this because you move forward with your design, how to deal with a real task with the exoskeleton, and
Mm-hmm.
I totally agree. We need to detect what's the environment, where is placed the exoskeleton with the person, how to deal, probably switch with a specific control strategy. Yeah.
Yeah, I think it's nice that it's competition based as well. I think it helps drive innovation. It's kind of maybe similar to how, I don't know if you watch Formula One, but my wife and I were big fans. And so, like, for example, the cars in Formula One and the engineering teams that work on these cars, these are super high performance. And this helps drive innovation. And eventually, not immediately, but eventually, this has a trickle down effect to like cars that are more economical that the everyday person would be using. But the technology that's being developed for F1 eventually does have this trickle down effect where you develop the technology, then you can then make it more cost effective and more affordable so that you can put it into cars for everyday users. Possibly this may have a similar effect where we're developing high performance robotic technologies and we compete under really strenuous conditions, and it's high pressure environments. They're very challenging as well. And by using this kind of competitive platform, hopefully it drives innovation, and then this maybe has a long-term effect in terms of what is rolled out eventually in terms of commercial products for everyday users.
But even with the technology, we need to improve some safety conditions. Last week, I went to some presentation. Some people working with law and exoskeleton. That's we're interdisciplinary group. But yeah, they talk about what's the European regulation about using robots in clinics, and there is no specific law about it. And we're creating new jobs with this. People who hang the exoskeleton, what's the properly way to lead in the patient using the exoskeleton. That's actually right now there is no an official job with this. So we are evolving with these technologies, and also we have to create multidisciplinary groups. That's a really good approach with this kind of challenge like Cybertron. You are not working only engineers, only medical. You have a really good team to create a really responsible technology.
Mm-hmm.
That's really good, and that's what I'm watching with your experiments. You right now are working in University of Toronto, and you have access to, I don't know what your plans right now, but probably using technology with the patients, as you say, with neurological patients, cerebral palsy, let's say, for example, and you need to have a really good experience from the exoskeleton to the patient.
Yeah, we had the similar thing in Toronto, kind of like you mentioned, to what you have in Spain. At the University of Toronto, it's very multidisciplinary, but I'm also affiliated with the Toronto Rehabilitation Institute, which is a hospital, which is part of a kind of a larger hospital network within Toronto. And it's quite extensive, actually. It consists of like, I don't know, maybe 5 or 6 other hospitals. And there, you literally have physicians working with occupational therapists, working with computer scientists, working with neuroscientists, working with engineers, working with kinesiologists. It's very multidisciplinary, and that's a unique aspect. When I was at the University of Waterloo during my PhD, I was surrounded by primarily engineers and computer science. The University of Waterloo is a very technology-heavy university. It's very technically focused, which is great. The level of technical ability coming out of the University of Waterloo is unbelievable because they really emphasize the the engineering, the technology, the technical capabilities of their students. Now, translating that to Toronto, where I'm now working in a physical hospital, we're now seeing, okay, there's the technology, but how do then users interact with this technology? What is their preference? What are their concerns? What are some of the things that they're most interested in getting out of it? What is their perception? Just looking at some of these robotic devices, you don't necessarily have to be an older adult or somebody who has a neurological condition to look at these devices and be like, maybe I don't want to wear that. Like maybe I'll feel self-conscious. You never know. And that's another thing about working at the hospital, is that it opens us up to being able to explore a wide variety of users. This is something that I don't know if those who aren't involved in exoskeleton research appreciate, the broad applications of the technology that we're developing. Exoskeletons can be used for primarily three different things. One is augmentation, one is assistance, and one is rehabilitation. Augmentation exoskeletons are wearable devices used for people who are primarily healthy individuals and that want to achieve some level of kind of quote unquote superhuman strength. This could be soldiers, firefighters, search and rescue, military users. And so that's one class of exoskeleton. Another class would be assistance. So this is exoskeletons that are used for actually helping perform some type of movement. So a user wants to stand up from a wheelchair, stand up and be able to walk. An exoskeleton can be used by these individuals to stand up and do that. A unique aspect of these devices is that they can also be used for rehabilitation over time. So as the user is using them, they are regaining strength, they are regaining motor control through neuroplasticity, and all of these therapeutic benefits of also wearing the exoskeleton. Now, if we're talking on the medical side, I did mention there are three classes. One class is augmentation, that deals with a quote unquote healthy population. The other two classes deal with more of the medical aspects, and that's what I'm most interested in. Now, you did mention a few potential users, which would be individuals with spinal cord injury or children with cerebral palsy. And these are often the most thought of when people think of these types of devices. But that's actually a very small percentage of the people that actually have the potential to benefit from these. There are larger worldwide demographics like individuals with Parkinson's disease, or even more prevalent would be people with osteoarthritis. This is very prevalent, especially in countries where there are obesity epidemics and we're having this excessive loading on joints and bones. And in addition to that, probably the biggest population is the aging population, which also have other issues like, for example, osteoarthritis. The aging population is like, those over 65 years age, I believe, are around like 500 million right now. And this is projected to almost double in the next 1 or 2, maybe 3 decades. I can't remember the exact numbers. But yeah, whenever I'm talking to my friends and family about developing these technologies for end users, almost everyone thinks of spinal cord injury. And I would sometimes get a response saying, well, like how many people actually have a spinal cord injury in the world? And even though it is a small percentage of the kind of total population, it is important to realize that if you have a spinal cord injury, especially a complete spinal cord injury, let's say at the cervical level, your level of independence is very low. So there may be only a couple thousand individuals with spinal cord injury in Canada, but the burden, the cost of caring for these individuals is so high to our healthcare system because they have very limited ability to do things for themselves. On the other end of the spectrum is, say, just older adults with no other quote unquote disabilities. These are individuals that have some level of independence and some level of mobility, but there's millions of them. Like I said, globally, hundreds of millions. And so I kind of see within the exoskeleton space people moving towards developing technologies for these other demographics, like, for example, older adults or people with osteoarthritis, not just spinal cord injury. And so it's a really exciting time in the field where we're starting to look at these other patient populations and how do we design for them? How do we design new controllers for them? And understand more of all the unique challenges associated with these different demographics.
Brooke was saying that maybe we can use this exoskeleton with a more kind of pathologies or more scenarios. So could you continue with this topic?
Yeah, I was just saying that a lot of traditional exoskeleton research has focused on individuals or assisting individuals with spinal cord injury. And that makes sense because it's a very challenging problem and it's an obvious problem. These are individuals that are typically wheelchair bound, and it just intuitively it makes sense if we're going to design something to allow someone to stand up and walk, that it could be applied to someone with a spinal cord injury. But that actually is a relatively small percentage of the population that could benefit from these types of wearable robotic devices. Some other examples include kids with cerebral palsy. Some also include individuals who have Parkinson's disease. But perhaps two of the largest populations that could benefit from these types of wearable devices are individuals with osteoarthritis and the aging population. So, for example, I believe that the global prevalence of individuals over 65 years of age is about 500,000, and that number is projected to significantly increase. Sorry, actually, that's not even correct. It's not 500,000. It's about 500 million individuals worldwide. And that number is projected to increase to approximately 1 billion individuals over the next 1 or 2 decades. And so if we can design exoskeletons for individuals that require partial assistance, not complete assistance, which is often the case in traditional exoskeletons for those with spinal cord injury, but the ability to provide partial assistance. And in order to do that, or one way to do that, is to make advances on not only the control side, which is what we've been talking about thus far in this podcast, but also advances on the design side. And this is also some of the work that I did in my PhD, where we're looking at the possibility of actuators that allow for what's referred to as backdrivability. And so this is in convention to traditional actuators used in, say, exoskeleton applications, where the motor is generating power in order to accelerate the user to allow them to stand up from a wheelchair, for example. Now, that's when the exoskeleton provides all of the torque, all of the power that's needed to perform a movement. Now, in cases like individuals with osteoarthritis or elderly individuals, they don't need support all the time. They do have their own volitional control, and they only need partial assistance. So there are some times when you want the actuators to be kind of passive. You want them to be able to move in the opposite direction. You want the user to be able to freely move the joints using their own musculature. And this is referred to as backdrivability. Now, one of the cool things is that when you're backdriving an electric motor, it has the potential to do energy regeneration. And this is something that Elkin and I, we've been talking about during my PhD to see whether or not we can explore this using the Technaid exoskeleton as a platform to study the potential for energy regeneration during certain activities. And I really appreciate you helping us out with that. That was actually really beneficial. We did talk to several other companies about the potential of doing that. And I learned that not a lot of companies like the idea of you backdriving their motors because that has the potential to overheat them and then maybe cause damage. So good for you guys for putting faith in us to allow us to do that and to work with us. That was really beneficial. And at the time, we were looking at how much energy could be regenerated when you perform movements other than level ground walking, for example, sitting down into a chair. So we were, driving the exoskeleton and kind of quantifying and characterizing its efficiency, both the motor and the transmission. And so these actuators that allow for backdrivability, I think are going to become more and more popular because it's expanding to areas that, like I said, allow for partial assistance in the case of users with some volitional control, for example, older adults. And so it's interesting that, and correct me if I'm wrong, I believe the Technaid exoskeleton was primarily designed for spinal cord injury and stroke, I believe.
Yeah, you're right.
But it has the potential to be applied to other populations because it does have a degree of backdrivability. Now, I'm sure if you wanted to move more in that space, all it would really require is some changes to the design in order to make it more suitable to the other populations. Have you guys been talking about that, about possibly like your demographic as to who would be using, say, the Technaid technologies?
Yeah, actually, I'm thinking right now related what we were talking before about the levels of contour. I think here we have another kind of high level where you create these therapies. Right now, here is a guy who's performing, is doing his PhD, and he's trying to use the exoskeleton with rehabilitation therapies. So he's studying what are the needs from people to rehabilitate. Yeah, not only with the classical pathologies, also what we need in the clinics. Because as you said, we can use in rehabilitation. We can create a specific exercise and a specific activity, getting some biomarkers, improving the performance of the gait even, or in a classical approach. Yeah, you said we can mix this information, use the back driving, create this therapy. I think is really interesting, and we're working right now with this.
Mm-hmm. And what specific populations were you thinking of?
I'm not sure right now what's the population because we're involved in some projects. One is with the aging. We want first to know what's the population we can work in. Yeah, because
Mm-hmm.
we know our focus right now is research, mainly clinics and research group, but probably we can move our technology forward with another kind of application because we know as a researcher we have let's say a low population using the exoskeleton, but probably we can move to another market.
Mm-hmm.
But we definitely know we need to create a really good benchmark with exercise or rehabilitation therapies.
Mm-hmm.
Yeah, we're trying to follow a really good safety indicators, what's the state of the recommending, and improve our device.
Yeah, so I kind of want to ask, kind of building off of that, does any of that relate to your PhD? And what is your PhD around? Because I know that you're also obviously working in the exoskeleton space, and you guys are doing work over there in Spain. So I was just kind of curious as to whatever you can disclose, what is your kind of PhD focused on? And any of the work that you're talking about right now, is that at all included in some of your work?
Yeah, not exactly related with the exoskeleton, but my PhD is related with the other company product that is the motion capture system based on IMU sensor. So one big problem with this sensor is how to deal with magnetic environments like buildings, even with the exoskeleton. That's what I say, not directly related, but we have this problem. We have to deal with this problem when you want to place an IMU sensor in an exoskeleton, you have some current, and obviously you have a bad estimation of the orientation. So one of the products of my PhD is how my algorithm can deal with uh, these problems in the magnetic environment. So it's really cool that my project can use the IMU sensor even if you are working with some structure like exoskeleton with ferromagnetic elements.
Hmm. Yeah, that's interesting. I'm like somewhat familiar with how challenging working with inertial sensors can be. As I mentioned at the beginning of the podcast, for my second PhD, I was developing computer models for simulating human motor control. And in order to validate these simulations, because they're fully predictive, it was grounded in forward dynamics and like optimal control theory. And in order to validate our simulations, we needed some motion capture data, or at least that's what we decided to do. And we used basically a full body suit that uses IMUs. And in order to account for, say, drift, for example, which is a common problem in IMU research, the software essentially develops an underlying dynamic model of the human, and the drift of the inertial sensors goes back to the model. And so the underlying biomechanical model is essentially used as like a framework for controlling the drift within the connected IMU system. This is the company that manufactures that software is Xsense. I'm sure you're familiar with them. And so, yeah, I am familiar with some of the challenges associated with working with inertial sensors.
Yeah, it's really typical and it's really good. In my experience, I think it's suitable to work with the IMU sensor even if you're working with these challenging environments. Actually, some guys from Shirley Ryan are using our IMU sensor with the exoskeleton, and they are predicting the specific gait phases to perform some specific controller strategy. So they are switching in some middle or low level controllers depending of the phase gate.
Yeah, that's actually a very active area of research.
Yeah.
It's almost shocking that not shocking. It's interesting that that is still a problem. There are still many research labs trying to tackle that challenge, where you're doing like gait estimation using maybe a single IMU or several IMUs, and it's still something that it still presents quite a large challenge for the research community. And so and yeah, I am familiar with the team at Shirley Ryan. They do phenomenal research there. I actually just got back from a conference in Arizona. It was the Wearable Robotics Conference, and there were several of the scientists there from Shirley Ryan that were presenting some of their research. And yeah, it's fascinating that it's still presenting a problem, but that kind of makes it in some ways exciting, because it's a really hard, challenging thing to solve. And as researchers, that's kind of what we're most interested in, is trying to solve these challenging problems. And I think IMUs in particular have so much potential because they're wearables, and wearables can be placed at various parts on the body. They have multiple applications well beyond just wearable robotics, like prosthetics and exoskeletons. They can be used for a whole host of different movement analyses and assistive devices, or even just commercial devices for data tracking. I know, I believe some of the wearables that are used for tracking activity throughout the day that can be purchased from big tech companies. I believe they use IMUs as well. IMUs are obviously used in your phone, and so I think with the proliferation of kind of the Internet of Things and connectivity and big data science, I think you're only going to see more and more development being done in the space of developing lightweight, efficient, and like robust and accurate wearable sensors, and have them kind of widely available.
Yeah, because in my experience, for example, when I start working with biomechanics, my first approach was a simple face detection, gait face detection. Yeah, and I create my database, identify what's the typical ways to segment the gait. But yeah, that worked really good with healthy ones. But when I start working with pathology people, the problem change. So
Mm-hmm.
I totally understand that this is an uh, open problem right now, and many researchers are working about how to deal with different kind of gaits. Even if you compare, let's say, just the gait performance between women and men, it's totally different. The way to walk is different. So in this regard, right now, later I can share with you, we're working in some simulation process. We're working with ROS environment, and we're trying to create an automatic segmentation of the gate and reproduce in some simulation environment like a civil. And we're trying to deal with this. It's really interesting, this work.
Mm-hmm. Yeah, and this is kind of like the parallel between um, exoskeletons and assistive technology, and people work in that space, and the biomechanics people that work in the biomechanics space. And we're now kind of seeing the bridge between the two, whereas now roboticists and biomechanists are kind of working together because they're using similar sensor technologies like IMUs, for example. Whereas previously, maybe historically speaking, they've been kind of separated, where movement analysis people would focus just on movement analyses within like a gait clinic, and the robotics people would just focus on the robotics. Sometimes also just in the lab because they were tethered systems. But now we're starting to take these exoskeletons and robotic devices out of the lab and into the real world. And same with the biomechanics. We're no longer limited to a motion capture system that's mounted to stands within a laboratory. We're now taking that science out of the lab and into the real world.
Yeah, it's really crazy to think about it. How when you ask why are you working with the exoskeleton, I was thinking, yeah, I my degree was about digital signal processing, pattern recognition. I used to work actually with Parkinson's disease, trying to detect using the speech signal. Then I moved to biomechanical analysis, motion capture system. Then I started working with the exoskeleton, and I found here with the exoskeleton a really good way to work with several fields. I mean, mechanics, electronics, electrical. A lot of people are involved with this design, and we're really trying to improve the world, I think, so with these technologies, because we can use not only in a small group of people. We can try to work with a lot of people, as you propose. There are many people interested in using this kind of device, not wearing all the day, but in a specific task, we can try to use it in a
Mm-hmm.
simple way. Let's say, for example, just using the hip, just using the knee. We need help moving some parts. We can use only the ankles, let's say. That's really good approaches right now.
Mm-hmm. Yeah, and I like that what you said just now, because it kind of relates back to how we started the podcast, where this type of work is very multidisciplinary. And so for listeners interested in getting involved in this space of exoskeletons and wearable tech and biomechanics or wearable robotics, um, I would recommend pursuing a field within the general science and general medicine or general engineering. And it requires like a lot of people from many different domains. So you kind of got to find out like what you like, and see whether or not that kind of like fits within the scope or how you can contribute to the development of these devices. And so, yeah, like if you're asking for advice on what type of engineering discipline to get into or something like this, there's no really right or wrong answer. All disciplines are required. And like I said, it goes beyond engineering, computer science, it goes to occupational therapy, physical therapy, kinesiologists, it goes to many different disciplines. And as you did mention at one point in the podcast, even to areas that are not necessarily in medicine or engineering, but in law and public policy.
Exactly.
And all of these other domains, because these are devices that, as they start translating into more and more commercial systems to become more prevalent and more pronounced within our general population, these types of issues are going to be becoming more and more important and relevant to kind of our daily lives. Like what it's like, say, even the cost structure of these systems, in terms of insurance, in terms of policy making, in terms of what is allowed and what isn't allowed within certain domains. We see this in robotics, where people are talking about like the ethics of robotics or the ethics of artificial intelligence. I don't think that's really translated yet into the exoskeleton field. People, in my experience, this is at least not talked about a lot, but I can imagine that like the ethics of these types of wearable robotics will become more and more prevalent in the years to come.
Yeah, I really like this field because when you release a new technology, you have to be really responsive. And you cannot pretend you know all this thing. You will create a really safe device. You need to consider what's the environment, what the law think about, what the healthy people know about this technology. Okay, now let's talk with the mechanics and electronics, create a really safety and secure technology. I really love this part of my job when we are involved with multiple multidisciplinary people. I receive all this brainstorm and thinking about what's the future of a product. I really enjoy this kind of spaces.
Yeah, same.
Yeah, we learn a lot with these kind of discussions because, for example, you think, no, I can create this controller walking around the stairs, and you don't think about really, really safety for not even the patient. I mean, for example, the people who is helping with the exoskeleton. What's the risk of those people? Yeah, and last time somebody asked me, and I said, I don't know. Honestly, I don't know what are the risks, but it's really good to receive this feedback because we can think about this. What's the properly aids, not only for the patient, but for the end user, how to use properly our device. What's the policies here? How to use, creating a user manual really responsive, taking care of the patient and the clinic people. It's really good to receive this kind of feedback. Yeah.
Yeah, I can see that type of work, especially being done in a commercial setting, because this is something obviously that you're going to want to prioritize. So like at Technaid and like other exoskeleton companies, I can imagine, because you're dealing with the end user, because you're dealing with commercial systems, these types of questions become more pertinent. It'd be nice if that eventually starts. It'd be nice if that also translates to research, and like in the research lab that we're also studying these questions as well and conducting the science and doing the studies to be able to evaluate like what is the risk, for example, and to be able to quantify that risk so then we can inform policymakers, we can inform insurance companies, and then we can also inform like the commercial entities, just like Technaid. Yeah, I agree. I don't see too much of that being done right now in the research labs, but I can imagine that within the companies themselves that are manufacturing exoskeletons, I'm sure that these conversations are being had.
Yeah, I totally agree. I really want to, after my PhD, try to work in this field. what's the next steps or this technology, how to improve this in terms of technology, safety, healthcare. I really want to work with this.
Hmm. That's awesome.
Yeah, I think that's the future with this. I really enjoyed this time. Hey, Brooke, I really enjoy this moment with you. Thank you so much for all your time and support. And let's see if we can have another meeting, another podcast with us.
Yeah, thank you. And I do want to say thank you, like not only to the company, but then also yourself. Like I mentioned in the podcast, you and I, we did spend a lot of time speaking back and forth. Your help was you did help us out quite a bit during my PhD, and it's great. I really like that. I think this is perhaps a nice example of where university, so academia and industry can work together in order to explore different problems. And yeah, the assistance that we got from you guys, especially yourself, was great. Just like setting up the device, any questions about some of the underlying architecture or the actuators or whatever it may be, it was really beneficial. And so it was a great experience. And yeah, I just want to say thank you. I really appreciate it. And I'm looking forward to hopefully working with you soon.
Thank you so much. It is, and it was a pleasure to receive this kind of comments. And anytime we can help our customers, we will make it. We will make this kind of meetings, discussions, improving our system and improving your experiments. That's the thing.
That's awesome.
Okay, Brooke, have a good day.
All right, take care.
Bye.